Thank you for tuning in. So, how many of you have heard of the late Colonel John Boyd? Not many, I suspect. So, I'm going to begin with a story. It is the 1960s, and Boyd is getting ready to deploy to Vietnam. Boyd had been pulling strings for this assignment, but at the last minute, he gets new orders to come to the Pentagon to evaluate the initial design of the Air Force's new FX fighter. The Air Force wanted to replace the failed F 111 and do so quickly before they are forced to accept another Navy fighter like the F 4. Boyd didn't need a lot of time for his evaluation. Boyd's words to the generals: "I have never designed an airplane before, but I could fuck up and do better than this." Boyd expanded his EM theory to go from evaluating existing fighter jets to being used to design new fighter jets. The first result was the F-15, a jet that would dominate the skies for the next 30 years and achieve a 35-0 kill ratio in the first Gulf War. In part 2, we will look at Boyd the author and Boyd the jet designer. We will apply what Boyd learned from these experiences towards operator training and DCS design. After the Korean War, Boyd was assigned to the Fighter Weapons School at Nellis Air Force Base where they trained pilots. Boyd soon realized that there was no formal training for pilots. During the war, pilots learned through trial and error as they worked their way up from wingman to flight lead. Those that did not get shot down became expert combat pilots. There are rule of thumbs that were passed down, like beware of the Hun in the sun from World War I. In World War II, there was the tactic dive and zoom that Claire Chennault used with the Flying Tigers. The Navy pilots were taught the thatch weave tactic to allow one's wingman to get behind an enemy zero. Flight school was very light on classroom and heavy on flying, but the flying was heavy on navigating long distance and dropping bombs. Very little of the flight training was focused on dogfighting skills. Boyd took over the academic branch of the Fighter Weapons School at Nellis and set out to write a new textbook on air combat tactics. The result was his Aerial Attack Study. It was immediately classified. However, bootleg copies started being circulated by Air Force pilots all around the country. Boyd's book was written in the 1950s. To this day, there have been no additions to his book, which is considered the gold standard for air combat tactics around the world. So why is this important? At many companies, pilot training in the 1950s may be similar to operator training today, with a lot of on-the-job training, OJT, and little classroom training. The operators learn their job through a similar progression from laborer to top operator, just like from wingman to flight lead. There is a sink or swim similarity as well. Those that can't perform the job or can't advance are let go. There are similar rules of thumb for all operators. Don't start a pump without verifying in and out. Open steam valves slowly. And my favorites: can't push on a rope and water flows downhill. The foundational principles of chemical engineering. Operator classroom training is focused on government and customer mandated policies. Many companies have limited dogfighting training, like simulated alarm flood situation training. Many do not do formal training on cascade loop control or how to read sequence code. Many do not train on how to read and interpret a P&ID drawing. Many plants are challenged by having few accurate P&ID drawings, or the plants do not provide the operators access to the P&ID drawings. Boyd took on this challenge of how to improve fighter pilot training by writing the definitive textbook on air combat tactics called the Aerial Attack Study. He demonstrated the power of these air combat tactics in his feather-ruffling way by offering a challenge. He allowed any pilot to get behind him and insisted that within 40 seconds he could reverse the situation. If not, he would pay the pilot $40, which was a lot of money in the late 1950s. Boyd never had to pay. He earned his first nickname, 42nd Boyd. Boyd's work on fighter pilot training takes place before the Navy's Top Gun School was created. In the movie Top Gun, you see Tom Cruise in a classroom reviewing air combat tactics. This was Boyd's influence. In the movie, you also see Tom Cruise hit the brakes and let the enemy fly by in order to get behind them. This maneuver started with Boyd with his F-100 fighter and was one of the main ways he avoided paying the $40. So what would Boyd say about our training of operators? Boyd would say that classroom training needs to be the centerpiece of operator training. Training should focus on simulated situations of alarm flood events. Operators need to know all about the capabilities of the DCS. Operators need to know how to interpret hardware errors quickly. Is the error from a bad point, bad card, or bad processor? What do all the hardware error codes mean? Boyd would cover mass balances, how to read steam tables, how to read a pump curve, and other basics. If there were P&ID issues, Boyd would train operators on how to build graphics so they can make their own as-built P&ID style graphics for use in lockout tagout and operator training. Ultimately, all of this would lead to a Top Gun school for operators run by instructors drawn from the top operators from across the company. Not all Navy pilots went to Top Gun. Not all operators should go to Top Gun. Only the best operators. These Top Gun operators would become the leaders of safety and quality improvements in the plant. Given the menu of air combat tactics, the next problem for a pilot is to pick which is best. To understand that, Boyd realized that you had to look at the performance characteristics of your jet as well as those of the enemy's jet. The best case study was the Korean War. Boyd wanted to understand why the F-86 did so well against the MiG-15, which had better maneuverability characteristics. He found two advantages that the pilots exploited: visibility and hydraulic flight controls. The bubble canopy allowed the F-86 pilot to see the enemy easier and quicker. The MiG-15 canopy was described as looking through a Coke bottle. The hunt in the sun tactic was all about making it difficult to see the enemy. The bubble canopy made it easier to see the enemy. The hydraulic flight controls allowed the F-86 pilot to change directions extremely quick. The pilot could simply push the joystick from one extreme to another using just one finger. The MiG-15 pilot had to use their arm strength to manhandle the joystick to make comparable changes. Chennault's dive and zoom tactic was to avoid dogfights with a Zero by making only one pass at a Zero and then disengage quickly. The P-40 simply did not have any performance characteristic to counter the maneuverability of the Zero. Maneuverability has always been a key factor in fighter planes, and at the start of World War I, World War II, and the Korean War, the enemy had the advantage. To reverse this, Boyd went back to college to get an engineering degree. While in college, Boyd came up with the energy maneuverability theory, which could mathematically calculate maneuverability. After stealing $1 million of computer time, he had a theory capable of designing the F-15 and F-16, and for the first time, America had the most maneuverable fighter at the start of a war. The equation on the left is the EM theory, where maneuverability is all about energy. The plane that loses the most energy will ultimately lose the dogfight. So what would the automation equivalent be? Since Boyd is no longer with us, it still needs to be determined. Potential factors could be number of operator keystrokes during an upset condition, alarm count during an upset condition, or maybe system measurements like the number of operators per I/O point and percent of I/O not under sequence control. Any DCS should have enough bells and whistles to minimize all of the potential factors, as well as enough programmer support to fully utilize those bells and whistles. So how does all of this apply to automation? The DCS is the fighter jet of an operator. The bubble canopy, which allows the pilot to see the enemy planes easier, is akin to high-performance graphics, which allow an operator to see the specific problem easier, as it would be the only object colored on a graphic. Alarm management is also a form of better visibility because it weeds out nuisance alarms so that only true legitimate problems are called to the operator's attention. The heads-up display is commonplace in modern fighter jets and is starting to work its way into automobiles. For an operator, the equivalent is what I call the query display. We will do some in-depth discussion of the query display later on. The hydraulic assist controls are akin to fully automated sequencing. It takes a lot of manual effort to command individual valves and motors. An automatic sequence is one click and similar to the F-86 pilot being able to change directions by placing one finger on the controls. Boyd wrote the book on air combat tactics and is up to some new enterprising person to write the book on operator tactics. One possible title to such a work would be the Operator Attack Study. This could cover topics such as unit operation theory, reading sequence code and control narratives, DCS control loop design, and the use of P&ID drawings. Aircraft design history was changed by Boyd as his EM theory promoted different metrics as being best suited for air-to-air combat. The traditional specifications of altitude, speed, and range transitioned into change in altitude, change in speed, and longer range. Boyd's EM theory favored smaller, lightweight planes, which meant only a single engine and less new high-tech in favor of proven lower tech. Perhaps the most difficult of these new design requirements was the concept of a single-role aircraft. Boyd wanted to avoid the jack-of-all-trades, master-of-none approach of the McNamara era. The compromises for multi-role weakened performance in air-to-air combat. DCS design history was about getting more I/O capabilities on proprietary technology. Processor redundancy was a major selling point. DCSs were the embodiment of one-size-fits-all. A typical DCS is capable of running anything from a sewer lift station to a nuclear reactor. Development has been to increase vertical integration, to allow the DCS vendor to play larger roles in the automation of a production line. So what would Boyd recommend? Proprietary I/O would become multi-vendor I/O to allow competition to control costs. Redundant processors would become single processors to minimize cost. Many manufacturing plants have moved away from installing redundant pumps as a way to save maintenance expense. Same logic applies to single processors. A single DCS performing multiple roles would become a collection of single roles performed by multiple DCS systems. More high-tech and more vertical integration would become right-size tech and more horizontal integration. All of these are designed to control costs and to optimize performance. A DCS vendor is an advocate for their own proprietary I/O. This goes back to the beginning of the DCS. I/O companies like Foxborough and Rosemont and others created their own DCS systems. When a DCS vendor's I/O became obsolete, a company was directed to only upgrade with the newest version of the DCS vendor's proprietary I/O. The best way to control costs is to competitively bid. A Boyd DCS would interface with a wide variety of I/O families without losing any functionality. A Boyd DCS would not care if the equipment was wired to Novatec 8000 I/O, Emerson Charms I/O, or Rockwell 1756 I/O. For each new piece of equipment, competitive bids would determine the I/O selection. If Rockwell's PAX followed Boyd's principles, it would support not only 1756 I/O, but also Novatec 8000 and Emerson Charms I/O. Traditionally, no matter what the size of the unit operation, redundancy was provided. I believe Boyd would challenge that tradition. Like with jet fighters, Boyd considered and demonstrated mathematically that a single engine offers the best air-to-air combat performance. The two main reasons for redundant processors were to avoid production interruptions from software upgrades and from power outages. Technology improvements have made these two issues very rare. Component failures are even rarer, except for power supplies, which are typically redundant for all computer equipment. In Boyd's mind, the redundancy required a reason. The original design of the F-16 had superior air combat performance over the F-15. Ground attack offers more of a chance for damage from ground fire, so in Boyd's mind it made sense to replace the single-engine A-1 with the twin-engine A-10. In a plant, independent unit operations would be non-redundant. The cost of an infrequent production interruption is less than the cost in hardware and licensing for redundancy. Utilities touch multiple unit operations, and make the best case for redundancy. Unit operations that are dependent on other unit operations could be either. Boyd was fond of saying, challenge all assumptions. One of the long-time assumptions for many companies may be the insistence on redundancy. Rather than having the DCS support everything, a DCS is chosen by what it needs to support. If a DCS does not need to support something complex, then a lower functionality DCS can be used. Entry-level operators may use the lower functionality DCS, and as they progress to running more complex equipment, they may move up to using a higher functionality DCS. A legacy DCS from the 1990s may not have the advanced features needed for complex unit operations. An advanced DCS like Emerson's Delta V may be justified if APC functionality is needed, the process wants to utilize diagnostic information from the instruments to direct the automation sequences, or simulation is required for operator training and for testing all code changes. This might be our test example of a nuclear reactor. For very simple unit operations, a simple PLC or keeping it on the legacy DCS would be sufficient. This might be our test example of a sewer lift station. For something in between, like an evaporator, maybe a plant PAX or legacy DCS would be sufficient. You probably have gone through a similar analysis in your own life. You might be driving the high fuel economy Honda Civic as a commuter car. But for doing things with the entire family, you may have also purchased a minivan, like the Chrysler Pacifica. If you split the difference with, say, the Subaru Outback, you will have to accept worse gas mileage while commuting and less passenger space when going to places with the whole family. Boyd spent a lot of time arguing against the multi-role plane, which ensures that the plane is never superior in any category. In terms of a DCS, multi-role simply means underutilization, which ultimately shows up as higher cost. I believe Boyd would support more horizontal integration, less vertical. The picture on the left is the vertically integrated modern DCS. The picture on the right is the horizontal integrated DCS that supports multiple I/O platforms and multiple PLC platforms. But it also supports multiple asset management systems, or APC, or simulation. A Boyd plant may have two of these DCS systems running side by side in order to maximize functionality. Competition controls cost, as well as the right sizing of the DCS features to applications. Although it is fun to talk about all of the advanced features of a DCS, let's get back to the basics of how the DCS interacts with the operator. Earlier, I promised to go into further details about the query display, so this is it. All DCS systems have the three basics: trends, which allow the operator to predict oncoming trouble; alarm displays, which give operators warning to take immediate action to avoid an upset condition; and graphics displays, which show the current state of a unit operation or perhaps a summary of the production line. Alarm management and high-performance HMI standards can turn these displays from the Coke bottle visibility of the MiG-15 to the bubble canopy visibility of the F-86. But it is the query display which really sets up the operator for success. As I said before, this is the heads-up display. It varies from proactive to live to reactive. It will send a message statement to the display, but does not enunciate. Therefore, other operators in the control room are not distracted by these messages. The query display lets the operator know of trouble with a sequence like a failed limit switch. The display can be very specific in its identification. The query display could alert for less than economic conditions, such as a fouling reboiler. The query display could be alerting the operator that a sequence has hit a fork in the road and needs the operator to decide which direction to follow. The query display covers all parts of the operator's job, making it one level higher than a level 1 high-performance graphic. The query display will function like the radar screen of an air traffic controller. Planes not taking off or landing do not show up on radar, and neither would unit operations running at steady state. Query display tells the operator that a sequence is ready to start or informs the operator that a sequence has started. Once the unit operation is in steady state, there are no query functions. This is where the traditional DCS interfaces kick in. Once the equipment has reached the end of a run condition, like an ion exchange unit starting to see breakthrough in the form of rising conductivity, then an alert can go to the operator signaling a need to shut down a sequence. This could also signal to have the operator put the sequence into a queue for shutdowns that will automatically start the shutdown once tank space is available, or chemicals are ready, or chill water temperature is adequate. Once on the ground, the operator initiates turnaround sequences. These sequences also move into steady state conditions and will avoid the query display unless there is something an operator is required to do. Why not just use alarms? In a control room of 5 operators, every alarm for one operator is a nuisance alarm for the other 4 operators. A good operator will avoid alarm conditions via the trends or cycling fast enough through his or her graphics. Why not just use graphics? Advances in DCS and automation push more and more equipment onto operators. The query display gives one central screen that will have information necessary on all equipment under the operator's control. The operator does not have to go paging through graphics to find the problem. With some alerts, the sequences will stop so the operator acknowledgement of a query message can also immediately direct the sequence to take corrective action, i.e., the quick change in direction that the hydraulic control allowed for the F-86. So here's a picture of the operator as air traffic controller concept. The query display covers the TAN area. These include takeoffs, starting sequences, and landings, stopping sequences, as well as navigating the turnaround once the plane is on the ground, or in other words, the equipment is out of service. Southwest Airlines recognized that the company only made money when its planes were flying, so they did everything possible to minimize ground time. In terms of process automation, by routing all turnaround issues to the query display, which is under constant watch by the operator, issues can be resolved quickly, and therefore equipment can be put back into service quickly. Air traffic controllers use queues to prioritize takeoffs and landings. Operators can place sequences into queues so sequences can auto-start or auto-stop rather than wait for the operator to monitor tank levels or availability of utilities in order to manually start or stop them. Like with Southwest Airlines, equipment is only earning money for the company when it's in service. The right DCS, run by highly trained operators, can optimize equipment turnarounds. The right DCS, run by highly trained operators, can also run more equipment, thus increasing productivity. A highly productive operator is a key factor in the ability for a manufacturing plant to compete against the developing economy nations of the global economy. This concludes Part 2 of the Boyd on Automation series. In Part 3, we will learn about Boyd the inventor and how his OODA loop applies to process automation and in particular operator performance. I'm John Hauge. I hope you enjoyed this mixture of process automation and military history, 2 passions of mine. I thank you for your interest and your time, and I hope you will tune in for the next in this series.